My name is Bernhard Merkle. I'm working at ACCU. It is a company which has nothing to do with medical products or something like that, despite its name. We are doing sensors of all kinds. So here's a well-known example of a laser scanner. So you might know or already have seen this a car running around here with our laser scanners. Fortunately, the company who's using our scanners here has removed all our logos. So this saves us some thrown or broken windows. And we also don't take the pictures, but we measure the distance to the buildings so that you get this nice views in Google Street View. So they are running around with our sensors on top of the cars. That's one application. Another application, some guys of you have flown here, maybe. And there are these self-check-in terminals where you can put your luggage with the barcode, and it gets read automatically. And hopefully in the background, we also sort it on the tray so that it gets to the right destination. So these are scanners, 6 scanners, and they read your barcode independently from the position. Okay, that's just for the background of the company, and I'm doing research and development there in the Department of Software Engineering, and we also are responsible for tool chains for our developers. Short overview of the talk. We will first talk about some motivation examples, static and dynamic analysis. We will differentiate levels of analysis and shortly look at some books and tools. And then in the second half, we will look at Clang and implement an own checker and use some of the sanitizers, and then conclude with a summary. So often our life depends on software, and hopefully that software is reliable. However, if you look at the displays, sometimes it doesn't work. You can easily fix this with tilting your head. Sometimes it breaks a bit more. Sometimes it completely crashes. And sometimes there's no data left. Okay, you're still laughing now, yeah? Because you're still on the ground. So if you're sitting in the airplane, and for example, we also make sensors which life or people depend on. And if you're seeing a message like this, system is going down now in the airplane, please wait while your seat reboots. Fortunately, it's only the entertaining system and not the flight control system. Okay, so plane is going down now, yes. Okay, let's get back to serious stuff. I think there are, in most of the languages, there are traps and pitfalls, which we all have gone through. In some languages, they are even documented, like in the C ISO language appendix. There are examples, and they discuss unspecified behavior and undefined behavior, implementation defined behavior, and local specific behavior. Additionally, to these problems area where you can fall in, there are also things which can go wrong when you use the language, because you misplace things that the compiler doesn't detect. You omit something, or you add something you didn't want to add. For example, a equals sign, yeah. Well-known example, you compare things instead of assigning, or the other way around, and you have unexpected behavior and complexity. And these things should be detected so that our software is hopefully bug-free. We have also a lot of intelligent people who have written guidelines or best practices and collect them and publish them in books. So here's an example from Andre and Scott Meyers, older edition. They are also available for different languages. Even for Java, here is a collection of best practices And it's written by one of the authors of the Java collection library. This is Joshua Bloch. Yeah? So he's a guy who also implements part of the JDK that you're using when you're using the collection classes and the algorithms. You're using his code. And please remember his name. So because it's I have a red circle around because it will come again. Beside the books, we have also coding standards for security related things. You know all these attacks on infrastructure these days, on electricity, and the Computer Emergency Response Team has a coding standard for C. We'll also see that parts of it will be are implemented in Clang, and we have companies like Google who publish their C++ style guides, and I think most of you also in your company have some kind of coding guideline. And so who has their own coding guideline? Yeah. How many rules do you have? Over 10? Over 50? Yeah, still hands up. Over 100? Okay, who is checking it automatically? Okay, only a few people are checking automatically, yeah? And maybe also, I don't know, has anybody read the paper Power of 10? Does anybody know this paper? It's from Gerhard Holzmann. He is a leading guy of the NASA JPL laboratory. That are the guys that are writing software for the stuff that flies to Mars and the robots run around. And they have also a coding guideline, and it's the Power of 10. So they have only, essentially, or in his paper, he discusses only 10 coding guidelines for safety critical code written in C. So I think he has a valid point because he discusses mostly software development projects use coding guidelines. These coding guidelines are meant to state what the ground rules, blah, blah, blah. Curiously, there's little consensus on what a good coding standard is. I think you all know the discussions in your company. Among the many that have been written, remarkable few better than this kernel. The result is that most existing coding guidelines contain well over 100 rules, sometimes with questionable justification. And you know all this discussion about white space. I don't need it, that discussion. And he makes also the point that tool-based checks are important, since it's often infeasible to manually review hundreds of thousands of lines of code manually written for larger applications. Yeah? So taking the quote of worse is better, you can also say here for your coding guideline, less is better, yeah? Or less is more in a kind of sense here. Okay, so let's discuss some analysis techniques. We have one approach, which is static analysis. So we are analyzing our program without executing. So just the compiler goes through it and we try to find bugs. That has the advantage, we don't have to execute it, and we have no dependency on test case or even any test case. There are still people who don't do test-driven development. And static analysis looks for violation of reasonable programming errors. So it's not a replacement for testing, but on the other hand, it's very good for finding also problems on untested paths. But it has to be complemented with dynamic analysis because many defects cannot be found with static analysis. I think it can help to improve your code quality. Also, if you make your coding guideline into an automatic checking process, for example, before you do manual code review, you can find lots of bugs. And the advantage is that if you do it machine-driven and automatically, the process is very pedantic and reliable, because when you look at people in a code review, at some time you get tired, yeah? And you don't have the high level of attention all the time. And a machine can do that. This is what computers are for, yeah? Pedantic and reliable. Depends, of course, how large a rule set is. A result of the rule set will also be the number of warnings. And I get a lot of complaints about lint-like tools, that you get lots of warnings and false positives. We'll look at that. And the right errors are not found. Yeah, so that's one problem of static analysis approach. The other problem is, if you look at the books that we saw from, for example, from Scott Meyers, the question is, are those rules really tool processable? Because if you look at the sentences, there's no 100% or 0%, because he says strive for interfaces that are minimal and complete. How do you want to measure that? Yeah, I mean, you can do matrix, some kind of stuff, or prefer inline function versus macros, etc. There are always these corner cases, and I think part of the problem is that the out-of-the-box lint-like tools often do not know about your special environment and your special deviation of those rules. And if you apply a standard tool, then you have to live with these verbose messages where you say, I want a macro here because of that reason. Why does it complain? So I think there's static analysis is getting to the point where it really helps, but it's lots of improvements still possible and needed. Let's see different dimensions of static analysis. My first dimension is the checking technique. You can start with very simple techniques. For example, if you look at the third coding guidelines, they have several functions that are security attackable, which you should not use. String star copy without length, something like that. And the simple thing is just grab for these functions and you will find them. So a text pattern matcher like CPP check does, or your grab tool can find things. They cannot find all things, because if you're grabbing for C-style casts, then have fun, yeah, with regular expressions. You can't do this. So you need some higher abstraction, for example, the abstract syntax tree in your compiler. And this is where Clang comes in, because you can really access very comfortable the abstract syntax tree and write matchers for it. More advanced techniques are kind of symbolic execution. So we're still static analysis. You don't run the program, but you symbolic execute the states of your program and try to find a path where you access, for example, un-initialized variables. And I call these lint tools. We'll see example of tools later. Another question is the precision of the checkers. So we talked already about those annoying false positives. So your lint tool says there is a problem, but in reality there is no problem, because you made a deviation of the rule, or there's a special corner case, or you should help your lint tool because you know the input parameter for this function will never be null, so the error will not happen. The other problem is false negatives. So these are more critical. People don't usually complain about them because they don't see where the tool does not find it. Yeah, but it's a problem in reality, because problems are not found by your tool and they're in your source code. And I think you should not look at the absolute number, but on the rate of false positives versus all messages, or false negatives versus all messages. The second dimension I want to open is the level of static analysis, where you can apply this technique. The smallest level would be the micro level or the code level. So here we are talking about things like you should not do this, and not formatting of code, but you should always use braces around if and else, because later if you add something here in the else branch during maintenance and somebody forgets to add the braces, then you're in a problem because the added statement always runs. So you can check for this, and there are several guidelines like MISRA, etc., which enforce these rules. The next level, higher, I call it the macro level. So we don't talk about a single line of code, but we talk more about how do you write a real good constructor or a real good assignment operator or output operator. What rules do you have to follow? For example, do you have to return a new constructed element or a reference to this? How do I pass parameters? Do I pass by const reference or by value? Do you handle base classes? How do you copy the data? Do you check for self-assignment, etc., etc.? So this is just one example for, I call it macro or the design level of static analysis. And if you look at the rules of, for example, Scott Meyers, lots of them are on this level, I think. Then there's a third level, which I call the architecture level. So here we are talking about interfaces, components, subsystems, layers, and how they relate together. So how is the coupling? And you should, I think you should also check these things, because you have something like this here. This is your blueprint or your should architecture. How should the system be structured? Which interfaces do you access? Which are public? Which are private? How is the layer structure? And in reality, when you're really honest and analyze your system, and there are tools for that, you often see that the architecture has somewhat disappeared or gone, because some guy thought, oh, I need this functionality over here, just include the file, link with this library, and you are done. And the problem of cyclic dependencies comes up in your make system. You will notice that, but often some erosion happens, and yeah, you can't reuse parts of your system. And this also happened at our side. For example, we have yeah, no details. Okay, so you should check this, and there are also rules to enforce this. For example, only access 2 layers lower, or only access headers in the public directory or something like that. And I think you should check this also. There are tools for that. You don't have to do this manually. You can't do it manually. So we have kind of style checker tools like checkstyle or PMD. Lint-like tools of the first generation, I would say, also integrated into IDEs or into the Eclipse workspace. They are also available for different languages. For example, Findbugs is an implementation of a lint tool for Java and FXCOP for C#. And they are the second generation tool which does more these flow analysis, and for example, Coverity and Clockworks are tools from that area. And for the dimension of the architecture, there are also tools like yeah, CodeCity. Maybe you know this, CodeCity. They're graphically building, representing, for example, complexity in your or different matrices that you can specify. There are open source software like Moose, which you can extend also for different languages, and there are out-of-the-box solutions for specialized for languages and also for a range of language. For example, Bauhaus or Sotograph checks Java, COBOL, C, C++, and other languages. So here, just to screenshots of find bugs and lint integration in Visual Studio. Then we have dynamic analysis. We saw the drawbacks of, I think static analysis is very powerful, but we saw some drawbacks, and there are definitely bugs that you can only find at runtime. So dynamic analysis looks at your program while you are executing it or at the end of the execution. And of course, you should make sure that you traverse all the paths of your, or lots of paths of your program. So it heavily depends on having a good test coverage and good test cases. And so you should measure also your test coverage if you're using dynamic analysis. Otherwise, you don't know how much of your program you all actually traverse. Technically, it's instrumentation of the original code, either at compile time or at runtime, which adds, of course, some overhead, and sometimes significant, and sometimes it's so significant, for example, that it does not run on our small devices because we are restricted on stack and on RAM space. And so it depends what kind of instrumentation you have and what kind of overhead you have. There are some simple tools like specialized version of memory allocators. You have some commercial products like Bounce Checker, and Valgrind is very common on Unix platforms. So this is also a UI for it. So let's actually look at some bugs. That was a theory. Let's look at some bugs, how they happen in practice. And one commonism about bugs is that we programmers, we are smart, and smart people do not make dumb mistakes, yes? Of course. And we also have good techniques to find things. So we have pair programming, unit testing, reviews, test-driven development. So the conclusion should be, if everything is right above, that they are hard to find and susceptible, and that the bugs in production require sophisticated techniques. And I think if you followed a bit the Heartbleed bug discussion, yeah. You don't see this kind of bug. Yeah. What's the bug here? Yeah. Infinite recursive loop. Yeah. It will not be infinite. It will run off memory sometimes. But you say this is silly student stuff. So undergraduate. But then you look at real production code, which you have all on your machines. So somebody guesses where this comes from? So this bug is present in or was present in the JDK. And yeah, guess who wrote it? He's very effective, yeah. And in the Find Bugs Mag store, you can also buy a T-shirt with that bug on the backside. And Josh is not alone, so they implemented a checker and find bugs and found 5 other places within the JDK where the same bug happened. Yeah. And over different versions of JDK, it's about 25 times occurred. And in Google's Java code, so the guy who has implemented find bugs also checks the Google Java code, and they found, I think, 40 cases. And also in WebSphere, JBoss, Eclipse. That doesn't surprise me, but and Tomcat. So nobody's perfect, yeah. And I think bugs occur because of different reasons. Sometimes you just added two parentheses or a wrong Boolean operator, or you misunderstood a language feature or an API method or a class method. So these things happen. And well, we can turn on our compiler warnings, but the primary job of compiler is to make good machine code and not checking our bugs. But we can improve, I think. And Clang enables us to do this. So now we'll switch to Clang and have a short overview of Clang. So it's the project is Clang is part of the LLVM project, and it's a front end which compiles different languages. And it's a real modern compiler, so it has not a very long history if you look at the dates which are coming on the next slide. So the internal structure is very clean, I think. It's structured in libraries, and it uses object-oriented techniques, and it also supports new language features of, for example, of C++. They are very, very fast implementing things from the new standard. And if you look at the history, it's really not very old. It started with a student project, Chris Ladner, and then Apple essentially bought him, I think, and open sourced it. And since 2010, it's Clang is self-hosting, and it's also more and more becoming the default compiler in several Unix versions. So GCC is not the only kid on the block, but I think Clang is coming up, and there's some good competition. And competition also enables innovation and improvement in compilers. And I think I was unfortunately not here last year, but there was also talk about Clang Sanitizers and a keynote from one guy of Google who is working at optimizing Clang for C++. So these are the features, I think, of Clang. It's very fast compiler, it's a modern compiler, and the main point, I think, it has excellent diagnostics compared to other compilers. So they really care about compiler messages. We'll look at some examples, and it's extensible, yeah? And you can do a comparison with your Microsoft or your GCC compiler. For example, one thing is that you write code and you get back these long and cryptic error messages from your compiler, and you don't see where the error really is. And I think that's hopefully improving. So here's a small example of the FizzBuzz game, and there's a bug in it, which you might, does anybody see the bug? One bug. The first bug is the name. So it's actually not FizzBug, but it's FizzBug reversed. So we are nerds, and we are not counting upwards. So we are counting downwards here. And but let's just run the. If you don't see the error, then we just run it. Sorry?
It's going to get negative in your printing out.
Yes, okay. Somebody found it already. Yeah. So we have the problem is here the printf formatter is not consistent with the data type of the variable we are outputting. So you can say you should not use printf anyway in a C++ program. Then this bug does not happen. But actually, none of the compiler does detect it currently, and you only see it at runtime. Okay. So we fixed this, and we also fixed the semantic of the game. So I use now cout, and I count upwards, but there's a new problem in this program. Can you see it? Yes. Great. So this is the problem of the missing semicolon, and I think everybody has suffered from this. And we just look at different compilers now. Let's look. Yeah. And if you feed this to GCC, for example, you see it reports error on your for loop, expected comma or semicolon before the for loop. And if you look at the code here, so it's reported on this line here, but the real error is happening here. And maybe I mean, that's a toy example. That's the reason why you can find it that fast. But in reality, you have some macros between or some other code which has actually a semicolon, and then it's very difficult to diagnose this with this error message. Yeah, and the same is if you compile it with with the Microsoft compiler. It's also missing semicolon before yeah. And if you feed this to Clang, then it actually finds the real source location of this. So the diagnose is very essential for Clang, and they have even a own web page for where they discuss also examples. For example, you can enable the checking the printf parameters. There's a special operation, and GCC does not point to the location, and it's a problem if you have multiple format specifiers. You have to fill out it on your own, and Clang does detect it immediately. Here's a question.
Are you using a recent version of GCC? Because I thought they had caught up to that.
Yeah, they're coding up. Yeah, they're catching up. Yeah. So let's look. My GCC version. I don't know. -v. Sorry. Yeah. So it's an agent. So that's the default that comes with Ubuntu. Yeah. So I do not want make compiler comparison or blame GCC. I think there's some new competition going on, and compilers will catch up. Okay. So next error. What's the error here? Typo. Yes. It's a typo in the real world. And if you look at your code now, you have also a typo here. I think one of the most common typos you have that you misspell cout, for example. And as you can see, Clang also gives useful hints here. Sorry. Maybe, yeah. Yeah, so it detects that I've used dout, and it asks me, did you mean cout, and also points me to the relevant. Yeah. So you may say that's trivial, but I think it's really useful. Yeah, and it also counts when you go into more problematic area of the language. For example, if you look at this code. So you have a class with a virtual function, and then an inheritance with another function which is not declared virtual but which is implicit virtual. Then this stuff works here. Yeah. So it calls the appropriate method. But I mean, there are lots of people here which are C++ experts and in the committee, but if you use the average, the average C++ programmer which we have in companies, they are also a bit astonished that they don't have to put virtual before the inherited method. And I think it's also kind of inconsistent from the syntax side here. You should put it anyway, yeah. And the problem starts if you have.
That's because your code is wrong. Then the biggest problem.
Sorry?
Your code is actually also wrong, right? Because you need a virtual destructor if you don't have the.
Yeah. Okay. Yeah.
Sorry for the
Okay, but the real problem is this now. Yeah, if you have a non-virtual function and you inherit it from it and you override it with a virtual function, because then things really go wrong. Yeah? And none of the compiler is currently detecting this as a warning or as a error.
They use compiler also to detect it, isn't it?
Sorry?
The visual compiler gives you a warning that you are hiding the function. Yes. For like a decay.
That you are hiding the function, yeah. Okay.
Yes.
Okay. Okay. So we can, but to detect these things or other code errors, we can write now detectors with our tools in Clang, and there are different tools in Clang. One is Clang format. So anybody use Clang format? Okay, great. It's and there's a static analyzer, a Clang tidy tool, and a create tool, and we'll use them and now during the talk. So this is the overall architecture of these tools. There's a compilation database because most of the tools need information about the context, how the file was built regarding preprocessor defines and include paths. So this information is saved in a JSON file and this information is then pulled back by these tools, for example, by Clang tidy. Clang tidy has different modules, checking modules, for example, for the CERT coding guidelines or for the Google guidelines or for modernizing, and you can write own checks. There also is a static analyzer, which is more complicated in Clang, and the Clang format tool. So this is the information about the Clang compilation database. Essentially, your refactoring tools, for example, need the entire preprocessor context, and this is saved in a simple JSON file and is generated by CMake. So for each file which I compile, it saves the include directories and the preprocessor defines that I had on the command line at this time. Clang format is a very useful tool. It's a standalone command line tool. You can hook it up into your editor, and it has auto formatting for different kinds of languages. And it was recently extended also to cover Java and JavaScript and Google protocol buffs. And can, for example, also sort includes and implement different coding style guides. So there some are delivered out of the box, LLVM, coding guideline, and some of the other. So you just can format your classes in a very comfortable way. For example, I have here written a simple calculator class in JavaScript layout. So JavaScript layout is just the complete class on one line. If you look at JavaScript, it's in your browser, it's often because of performance inflated on one line. And if I use this with Clang format, it gets a nice layout and indentation and white space. So always use Clang format. It's a real cool tool. Then there's static analyzer. You can invoke this automatically via your build command, scan build. Does inject the compiler with the relevant options. And internally it builds a control flow graph and does a reachability analysis of your nodes in. So this is kind of that what these lint++ tools like Coverity are doing. So you're traversing through your program, and there are different kinds how you can do this. For example, it's the control flow graph, and then you can see this the bug occurs on a feasible path. Clang has several of these static analysis checkers. It can check for null pointer, address, null pointer, diff0, new and delete bugs, double free, use after free, etc. And you can also help to lower the number of false positives. You can help the tool with so-called source code or source level annotations. So here's an example of a program that gets a report. We have a different, so the Clang static analyzer reports here that you have a possible dereference of a null pointer, but the tool doesn't know that the semantic of custom assert is that it will abort. It will definitely abort, and therefore you can add an attribute and help the analyzer. So you feed in some additional information, and these attributes are also available, for example, for parameters. You can say parameter is not null, and then the relevant check is not flagged. So let's go to ClangTidy. ClangTidy is a standalone tool with libs and with checks, different checks, and they are modularized in different directories. So for example, the Google coding guidelines or the LLVM coding guidelines or things concerning performance and readability are all modularized in their own directories, and you can write your own checker, which we will done for our hidden method, our virtual method. So you can list these checks here. You can enable them on the command line, and there are lots of them in the current distribution. Another useful tool is Clang check. With Clang check, so the idea is before you write such a ClangTidy coding rule, you check the AST because you search for certain patterns in the AST. Yeah? And you can output the AST with Clang check AST term. For example, for our calculator, which had, let's look back here. It had two constructors, public method, private method, and some members here. And Clang check outputs the AST in a quite readable way. So you see here we have a constructor here. We have a C++ constructor tackle here with a void signature, with a constructor tackle here with a int parameter, so paramval tackle, and then we have a constructor initializer here. Yeah? So it dumps out the whole AST, and the idea is then when you write checker, you first write an example of your bug, then you dump out the AST, then you know for which tree nodes you have to search, and then you can implement a checker. So this is very easy, and it's a matter of a few hours, I think, writing your own checker. So to traverse this AST interactively, there's another tool which is called Clang query, and Clang query is also a command line tool with libedit support, so command line completion and history and stuff like that. And here you can interactively find AST matchers. So maybe we have a short look at this, how it works. Yeah. So let's do it just on our calculator class, yeah? Clang query calculator CPP, and because I have no compile database, I specified a --, and then I can query here the AST. So I am searching a matcher here, for example, for all param decal. It's difficult to write. Sorry. Yeah, from decal, and it finds all the places where param decal occur and underlines, and I can bind these matches later on and pass them. So that's the way you usually code your matcher. Yeah. So for example, here I have a more complicated. I'm searching, for example, let's assume I'm searching for return statements in functions, and the query is here. I search for function decals which has compound statements in them, and then I search all the compound statements, and within them I search a return statement and bind this to return. So root binds the whole, and return binds only this context here. So that's a really useful tool where you can first you use AST_dump to know what kind of node you're searching. Of course, when you are a Clang expert, you know all the classes, but as a normal user, you follow this approach, and then you query the stuff until you have found your matcher. So these are examples here. So let's review or write a checker for this bug, for this redefined non-virtual method. So there's also a rule in Scott Meyers' book. So never redefine inherited non-virtual method or declare overriding functions with override. I think then you also get a compiler hint. But unfortunately, this is the old GCC version on Cyclic, but there's no support for this. So we write our own checker in Clang. And first, unfortunately, writing your own checker, you have to build Clang itself. So download all the sources fortunately, they have a Git mirror, so you don't have to use the SVN. And then you build everything, and then you wait for hours. And then you go to a faster make system like Ninja, and then you notice that you're on Windows and have no read line lib, or you have it not yet installed on your Unix machine. Then you run the test, and the point is, it's not so easy to get that set up, and it would be, I think, really useful to have some kind of binary repository where you pull down the pre-built libs and the public header to write your own checkers. Yeah? That's a possible improvement for the future, and I'm currently setting up some Gradle-based make process for this, and that looks like quite promising. So let's write our first Clang check. So we have checked out all the stuff, we have built it, and the Clang tidy tool is located in this directory here. And then we have fortunately some Python script to set up the plumbing, and then we just fire off make. So we go to this directory, we add a new checker here. We specify the category where it should go in, for example, in efficiency, or in modernize, or in MISC, or in insert, and we name it, for example, virtual shadowing, because that. Yeah. And then the Python script already creates implementations, test cases, and a doc, and registration in a factory here, and it adds it to the make system. Next step is you try your checker, and it does currently nothing because you have to implement two functions. So implementing a checker is always following this rule you have to derive. So this kind of class is generated via the Python script. But you have to derive from a base class, Clang tidy check, and then there are essentially two methods. One is called register matchers. So here I register my AST matcher. So I pass in the thing I have determined in Clang query interactively via the console. And then if if matches are found, then the internal of Clang calls the check function. And in the check function, I can do additional things. Yeah, I can filter out candidates which are not relevant, or I can add a fix hint of that. So for example, the virtual gets added, or override gets added, or something like that. So two steps: implement register matchers and the check method. So to fill in the details for the check method, I first have to find a valid matcher, and the valid matcher is found. Usually I dump first. So I write a test case for that, then I dump the AST, and then I look for interesting nodes here, and then I fire up Clang query and ask Clang query here which things are problematic. Yeah? So the match here is I search for C++ method declarations which are virtual. Yeah? That's simply as it is. This query matches all functions which are virtual, yeah? And then they get underlined here. And then I do copy-paste programming. So I select this query here, and they have built a kind of DSL in Clang, which is exactly the same here. And then I just have to bind this node here to this identifier. Oh, sorry. So this is testing the check. So on the other side, we saw that test cases are generated, and I can, there's a special notation here for my test cases where I can say here, please assert that my Clang tidy check really issues a warning here and does not issue a warning here. So this is kind of a macro which makes sure that I get this error message on the next line on column 3 here. Yeah, this says next line, column 3. We talked about care about the message location. So I fire here. Here will be a caret, and then this error text here. You have additional macros here to check fix hints. So I could also offer a fix hint so that it auto fixes the location. For example, it could add an override word, a keyword. It's not a keyword, but yeah, to the location. So these are also other checks. So I fire off the make process and run the test suite. Remember, all the files were generated, and then I get here the failing test because the checker is not right here currently. So what the checker currently does, I put in the expression for finding virtual methods, and then my first check is I check if this class has base class, has no base class, then there's no problem. Obviously, then it was not possible to override this, so I can return. Yeah. Otherwise, it is an error, but this is not the right checker because there are test cases where this checks. Of course, I have to traverse the base classes and check if there are non-virtual functions. And this is the second check here. So I extended this check here. I check for all base class if the method is not a virtual method. And this is done here in this candidate predicate. So the check is here. So, and then I have implemented a checker which can mark those cases as error C++ code or wrong C++ code. So it's not hard to implement such a checker. I think you saw it. The other kind of testing is dynamic analysis. So there are these kinds of problems with sometimes occur, memory leaks, overrides, use after free, and there's a whole tool for this. These are the Clang sanitizers. They are separated in different tools. So the approach is do one thing, do it as best as you can and as fast as you can, and it's based on the LLVM code, and the overhead compared, for example, with Valgrind is really not that big. And these are the sanitizers which are shipped with Clang. You have sanitizers for undefined behavior, for thread problems, for address, and for memory problems. And there's a very good talk from Ismail, which was last year, which goes into detail of these Clang sanitizers. So I will not go here into details. I have just some examples. What is detected by these sanitizers, for example, for undefined behavior, you can detect these things here. I think we can skip these. So, Clang tidy can also be used as a refactoring tool. for example, to transform your old C++ code to the new style. And you saw that you also can implement automatic fixing. So fixins are essentially put out on the console here. And there are several checkers which are in a modernized module, like you should use auto, you should use range for each loop. So there's a loop converter which converts iterator-based loops. You can there's a check for usage of default and for override. So this is your old C++ code, and you can modernize now this code when you apply these checkers here. So there are checkers for modernize use auto, a loop converter, and an override, and the usage of default. And there's one missing, so to delete implicit generated method, you normally use that approach that you either inherit from boost non-callable, or you define your assignment operator and destructor private and do not implement it. That's the usual pattern you do, but you can replace this now with delete. And it is also a rule in Scott's new book here. So I think it's associated with item 11 and item 17, prefer deleted functions to private undefined functions. So we should use that new language feature in C++ 11 and convert our old code to use the new language facilities. And actually there's even a bug open in the LLVM bug tracker, because the checker for delete is missing. And implementing that is very straightforward. So essentially it's this Clang query. I've added that test here in my installation. So I've created a modernized use delete method text, and here's the Clang query on the AST for the matcher. So I'm searching for example, for constructors which have no implementation. Yeah. Yeah. Question.
How does it work across translation units? I have that in a header file, and somewhere I have that.
Currently, it does not work across translation units. Yeah. Mm-hmm. Okay. But out of the box, it does not work. So this is the matcher here for, and then you can here implement it.
For these fixes,
yeah.
For the fixes for going the other way as well. If you apply auto and delete the constructors as well, and you realize that you need to revert all that, go back to the prior version.
No, there's version control then. I mean, you have to go back. Yeah. Yeah. Also, there, when you apply fixit, it's not. So the approach is you get to the source code location where the fixit should happen, and then you output plain text. Yeah. So there are not adding that stuff in the AST and then dumping out the AST, because that would be too complicated, or there are too many invariants in the C++ AST where you can get it wrong. So applying the fixed is not so easy like writing these matches. Okay. So we are a bit ahead of time. I plan to show more of the. I'm not sure. Should we go into the implementation of the checker, or? Yeah. So we can add a checker and look how it works. First, a summary. So if we find now a bug, I think it's possible to implement a checker. It's also possible to implement your coding guideline and not only the lint standard checks. And there are also the sanitizers which trace these bugs which are happening at runtime. And the key thing is, I think, also to automate this process. So run it in your Jenkins build server, run the test in the build server, analyze the output, and maybe even some companies are even enforcing running the static checks or checking coding guidelines before you push it into the version control. And our experience was that it pays off very fast. And it's really worth doing it. I think also with Clang you have now an extensible framework, and you have real good tools at hand. Okay, we can go into the and look like this works. So here are the tools that we discussed, and there's a Clang tidy, and you start here with adding new check, for example, for yeah, something like this. Return early if we want to, for example, checking preconditions in function, and then return immediately if the parameters are not valid, something like this. Yeah? So this Python script does all the plumbing here. It adds first implementation of these checkers, and it's adding it to the make system and to the documentation. And then you can even run the build process and run your test cases. Let's look how the stuff looks like. So we have here turn early. So here you see the two checker methods register matcher and the check method. And there's even an example in it, which you have to, of course, modify with the values you found via Clang check, ASD dump, and Clang query. And if you find then matches here, the check method is called, then you can get the match declarations back and apply additional checks like we did it with our virtual function case. Yeah. This is the diagnosis here for the compiler, and this is an example of the fix hint where you then can create the correct version. And there's also a test case generated here. So the name was misc return early. And here you see these macros, which are then tested via the checking framework here. It checks for messages here, and you can also check for fixes here.